then for each iteration, we have orphan complexity in the symmetric case. For the Heisenberg form, we have n squared complexity, but it's still much smaller than n cubed. Okay? Yeah, so that's just a reminder how QR iteration looks like. We start from the original matrix, we factorize it using QR decomposition, and then we take the product in the opposite way. So, and this matrix AK has the same eigenvalues as the original matrix, has the same short form, and at the end it will converge to a triangular matrix in the general case, or to the diagonal matrix in the symmetric case. So, if the original matrix is tridiagonal, all the matrices in this iteration will be also tridiagonal. We can try to prove it. So we can look. It's a simple test. So if you just plot the sparsity pattern of the matrix, the sparsity pattern of the matrix, if the matrix is small, you represent your matrix as an image and put basically black pixel where the element is not zero, and white everywhere else, so you can look at this way visually, you can visualize the sparsity pattern, and this kind of information is often quite useful. So when you go to large matrices, it is a question how you visualize it, because if the matrix is million times million, how to visualize the sparsity pattern? Okay, you can do that still, but this is a very useful visual interpretation of how the matrix looks like, which is probably the first thing you have to do when you have a new sparse matrix, plot the sparsity pattern. So, yeah, and it's really, you see that the original matrix was tridiagonal, and the one was not tridiagonal, but the Q factor for example, just a Q. So the Q factor is actually not tridiagonal, and if we were computing all these elements, we will need to have n squared operations. But again, the good thing is that we can compute for the tridiagonal matrix. We do not need this matrix, and we do not need this matrix in the iteration. We only need, given AK, we only need to compute the final result. And then it is possible to implement an algorithm which is called implicit QR algorithm, implicit iteration, where you compute AK plus 1 from AK for a tridiagonal Heisenberg matrix AK without computing factorizations. Otherwise, the complexity will not be O of n, it would be n squared. And why should we do that? So that's what is summarized in this slide. And this is called implicit QR step. So a good implementation of a QR algorithm for a tridiagonal matrix never computes QR factorizations directly. And there is a theorem that justifies that. So the theorem says, so what we are doing? We are doing an initial matrix, and we are doing this unitary similarity transformation. And at some point in the end, we get a Heisenberg matrix. So we can do it, for example, using Householder transformations as we described several minutes before. So we do something, we multiply, we get this upper Heisenberg matrix. And the theorem says, if you know the first column of Q, then it defines all other columns. It's actually a very nice this is a very nice thing, because so you have Q star AQ, because it's related to the graph of subspaces, which we will discuss later on. So it again seems like a quadratic equation for the elements of Q. But thanks to linear algebra, we can do it better. So we have, in fact, AQ equal QH. So this is equivalent. So this equation and H is upper Hessian. Hessian-Berg. So we have to represent our matrix, for example, Q as 4 columns, Q1, Q2, Q3, Q4, right? Then A times Q equals, we just multiply AQ1, AQ2, AQ3, AQ4. That's okay. So upper Hessian, in this case, is again the matrix which has zeros only here. We'll draw this again. So if we multiply, then we need to multiply on the right side of this equation, we need to multiply Q by H. So Q times H, again, is Q1, Q2, Q3, Q4, times this matrix. So if we multiply this row, multiply this row by this column, you see that there are zeros here. There are zeros in the third, and there are a lot of zeros. So it means the first column of this product QH is just some number alpha 1 Q1 plus alpha 2 Q2 and something else. So what the theorem says, and we have the equation that AQ1 equals alpha 1 Q1 plus alpha 2 Q2. So that's the equation we have. And therefore, if we know Q1, then Q2 is just given by AQ1 minus alpha 1 Q1 divided by the normal of this guy. Okay? And that's all. So if you look at this equation, A times Q equals Q times H, so it actually encodes a certain recurrent connection between the columns of Q. If you know Q1, you can find Q2 and so on. So you only need to find Q1 to find out you only need to find Q1 to find out the whole matrix. So the whole matrix is defined only by the first column. And we actually computed this matrix, right? So if we say that we have AK equals QK RK, AK plus 1 equals the product in the opposite way. So in the QR factorization here, we do not need to compute the full matrix actually. We only need to compute the first column. And that's something nice. So I will not go into the details about convergence of the QRL because, well, it's really a delicate issue. So you can look at the proofs and technique. I do not want to think you will be very impressed. So this is just a summary of the theorem about proof and the main fact. So since we are computing all the eigenvalues, but the convergence is still in blocks. So as I told you last time, so the convergence is done like the first, the largest, and so on. So the proof is basically based again on the block splitting. So we split a matrix. So we assume that the matrix is diagonalizable. We split our matrix into blocks, and we have eigenvalues. First part of eigenvalues, second part of eigenvalues, and two subspaces. And we assume that there is a gap between eigenvalues. So remember the convergence of the power method. The power method converges faster if the gap between the first and the second eigenvalue is larger. But here, if we analyze the convergence of the QR in this way, it converges like block power method, when we simultaneously iterate not one vector, but a whole subspace of vectors corresponding to the specific eigenvalue. So we assume that these guys are ordered, lambda 1, lambda n, there is a gap between m and m plus 1. So what we want at the end, that this matrix would converge to a triangular form under the QR iteration. So we do QR iteration, and we expect this to converge to the triangular form, but we measure at this point the convergence into the block triangular form, right? So if it's in the triangular form at the end, it should be block triangular. So what we need to study, we need to study the norm of this block after k iteration of the algorithm. And the theorem says that there is a constant that depends on everything, like the norm of the inverse and so on. But asymptotically, the norm of this block decays like q to the power k, and q is the ratio between these two eigenvalues. And whatever, and you can of course split the eigenvalues of the matrix in many different ways. And for each of the splitting, you have such estimates. So for example, if you have one large eigenvalues and all others are separated, using this theorem, you will see that the block corresponding to this largest eigenvalue will converge to 0 in a fast way. So that's how it's typically used. So, and if the eigenvalues are sort of equally spaced, then the largest will converge, the second will converge, and so on. So how to speed it up? Because the eigenvalues can be really close, and it's very typical that the eigenvalues, they are sort of almost a smooth function from their number. So what can be done? And that comes the idea of shift, which separates actually the algorithms for small, dense, full eigenproblem from partial eigenproblem. This is what we can only do for a full eigenproblem. Basically, removing any difficulties with this slow convergence. So what we can do, since the matrix A and the matrix A minus arbitrary shift, they have the same sure form, except that you also have to shift it, then the QR algorithm with shifts looks as follows. So you take the matrix and you factorize not A, but A that is shifted. Then again, let's go to the theorem that we discussed before. So what is the asymptotic convergence factor? The asymptotic convergence factor is then governed not by the ratio of lambda m plus 1 to lambda m, but with the ratio of lambda m plus 1 minus this shift divided by this. So that's what we have. So, and here comes one of the simplest ideas. So if we start our algorithm and we get, so the largest eigenvalue starts to converge, then we need to shift to the first converged eigenvalue. Then basically this will be very close to 0, and the convergence will, so this is a linear convergence rate. So asymptotic convergence estimate, they say the bound of the norm of k is less or equal than q to the power k. So if this factor is 0 or close to 0, it means you have superlinear convergence. So you have quadratic convergence. In fact, in the symmetric case, you may have even local cubic convergence. We'll discuss it a little bit later. So, and then the question is how to select this shift. There are different strategies of selecting this shift. And there also can be not one shift, but several shifts simultaneously, maybe 2. So you factorize not A minus Si, but A minus S1, A minus S2, and so on. So the simplest shift would be take the block that is already in the upper triangle form and take the lower form. So so-called Wilkinson shift, when you take a 2 by 2 submatrix that is located in the corner and find the corresponding eigenvalue of this matrix. So there are quite a few heuristics, and these heuristics are justified and they're also implemented, but we just need to know that real implementation uses shifts. So, what I said, but this shift only works because we can shift the full matrix, so we work with A minus lambda I. And we factorize this. So if you look at the power method, and the convergence rate of the power method, they're very related. So the convergence rate of the power method is lambda 2 divided by lambda 1, the gap. So it's like convergence of the first eigenvalue. So what We can try to use shifts here for the partial eigenproblem, but unfortunately, if we do the shift, so we cannot do, you can try to find optimal lambda, but still then you cannot improve over the ratio. So what you can do, you can try to find minimal eigenvalue like this, but the convergence will be quite slow. So there is a big difference. So in order to use shifts in the correct way for the iterative methods, actually you have to compute the inverse of the shifted matrices. Computing the inverses of the shifted matrices may be much more complicated. So, and this is the so-called inverse iteration. So,